work on to engineers' mindsets. So let's say we are doing this program to do the shear force and bending moment analysis and also draw the shear force and bending moment diagram. Okay, first thing, outline your free body diagram. Okay, so we have, notice that at point A we have a P, so that requires two reactions at point A, R, A, Y, and R, A, X. Okay. Between point A and point B, there is a UDL whose intensity is 2 kilonewtons per meter. And of course, to convert the UDL to a point load, multiply the UDL by the length covered. The length covered by this UDL is 3 meters. So 2 by 3 gives us 6. Then we place it at the middle of the length covered. So the length is 3 meters, middle of 3 is simply 1.5, which is 3 divided by 2. Okay, so we'll have 6 kilonewtons. This point B. So distance from here to here 1.5 meters. From here to point B as well as 1.5 meters. Okay. At point C, remember it is a ruler, another shape for a ruler. So for a ruler support, we have just one reaction normal to the surface. Okay, at 90 degrees to the surface, so we'll have R, C, Y, this point C. Okay, and at point D there is a force handling, and that force is 10 kilonewtons at point D. Okay, so we employ our equilibrium equation. From starting the equilibrium equation, summation of force in the horizontal axis is equal to 0. So summation f of x is equal to 0. That simply implies that Rax is equal to 0 because Rax is the only horizontal force that will have it. Also, summation f of y is equal to 0. We consider upward force to be positive, downward force to be negative. So that simply implies now that Ray is upward, so it's positive. We have Ray. Next, we have the 6 kilonewtons force acting downward, so it's negative, minus 6. Next, we have RCY pointing upward, so it's positive, plus RCY. And finally, we have 10 kilonewtons force pointing downward, so it's negative, minus 10, and this is equal to 0. Okay? So we can say this is minus 6 minus 10 is minus 16. So this Ray plus RCY minus 16 is equal to 0. So let's send minus 16 over to this side of the equation. And we have Ray plus RCY is equal to 16 kilonewtons. Okay, so let's call this equation 1. Alright, so we have two unknowns in the linear equation, which is impossible. So we take moment at point A. So take moment at point A. Okay, so summation of moment at point A is equal to 0. Let's consider clockwise moment to be positive, anti-clockwise negative. Okay, so as always said, if you take moment at point A, the moment of these two forces Ray and Ras at point A will be 0, because moment is force times distance. There is no distance between these two forces at point A. Therefore, their distance is 0. So it means 0 times Ray, 0 times Ras. So that's why we have that law. Moment about any point is 0. Okay, so we take moment of this 6 kilonewtons force about point A. Notice that this 6 kilonewtons force is pointing downwards. Therefore, the direction of moment about point A is simply this way. So which is what? Positive to our direction, clockwise, so it's positive. So this force makes a positive moment. And the distance it takes this force to get to point A is 1.5. So you have 6 times 1.5 to be the moment of that force. Okay, moment of RCY about point A, RCY points upwards, therefore it will go in this direction to point A. So going in this direction means against our direction of moment, so it is negative, anti-clockwise. And the distance it takes RCY to get to point A is simply from here 1 plus 1.5, 2.5 plus 1.5, which is 4. So distance against RCY to get to point A is 4. So we have minus RCY times 4. Times 4. And then finally, we have a 10 kN force pointing downwards. Moment of this force will go in this direction, which is positive to our direction. Positive, that's clockwise. And distance against this force to get to point A is the total distance of force to B. It's 1 plus 1, 2 plus 3, 5. So we have plus 5 into 10, and this is equal to 0. Okay? So 6 times 1.5 will give us 9. This will give us 9. Okay? Minus 4 RCY plus 50 equal to 0. Okay? So 50 plus 9 is obviously 59 minus 4 RCY equal to 0. So we send minus 4 RCY over this of the equation. 59 is equal to 4 RCY. And now to obtain RCY, we divide both sides by coefficient of RCY, which is 4. So that simply implies that RCY is simply 59 divided by 4. Therefore, RCY is equal to 14.75 kilonewtons. RCY is 14.75 kilonewtons. Okay, so knowing RCY, substitute into equation 1. So we have RAY plus, in place of RCY, 14.75, that's equal to 16. Okay, so RAY is equal to 10 plus 14.75 over to this side of the equation becomes minus. So you have 16 minus 14.75 kilonewtons. So it means that RAY is equal to 1.25 kilonewtons. Alright? So on obtaining RAY and RCY, we can now start the shear force analysis. Always we bring down the beam. Bring down the beam. RAY equals 1.25 kilonewtons. Remember, between point A and point B there is a UDL. So we also show that this point, the intensity of the UDL is 2 kilonewtons per meter. Okay. Okay. For a C, we have a ruler operated that made the reaction to be 14.75 kilonewtons, 1 meters, 3 meters, 1 meters. We have 10 kilonewtons, right? Yes. Okay. Now, this is going to be a little bit tedious and different from the first one because of the UDL starting from the beginning. So, okay, as always introduce your, whenever you see the UDL, there's always a need to bring in the shear force equation. Okay, so to do that, first of all, you must start a section just between the UDL, section XX, before going to the end of the UDL from point A, all the distance towards X, to the X. Okay, so shear force analysis. Alright, shear force at A is simply the force that exists at A. Upward force positive, downward force negative. At point A, there is an upward force of 1.25 kilonewtons. So shear force at A is 1.25 kilonewtons. So it's positive. Okay, this same force moves between A and B. So shear force AB will already have 1.25 moving. But between A and B, there is a UDL. So so that we need to form the shear force equation. We said from point A to the point of section which was x as the distance. So it means now that the point load, remember, if the distance of the UDL is x, then point load is simply the intensity of the UDL times what distance. In this case, the UDL load is 2 kilonewtons per meter. Distance now is x. Okay, so we have minus 2 times x. Remember, minus because the UDL load always points downwards. So when it gets to B, notice that x becomes the length of AB. If you finally move from point A to B, x becomes equal to the length of AB, which was 3 meters. So at B, x is equal to 3 meters. So therefore, shear force at point B becomes 1.25 minus 2 times 3. And this is equal to 1.25 minus 6. Okay, so shear force at point B is obviously minus 4.75 kilonewtons. Okay, so this same force moves from point B down to point C. So shear force at C is equal to minus 4.75. But notice that at point C there is an upward force of 14.75 kilonewtons. Upward, so it's positive, plus 14.75 kilonewtons. Okay, so shear force at point C is equal to, of course, minus 4.75 plus 14.75 will give us 10 kilonewtons. And then finally at point D, shear force at point D becomes, okay, so we have 10 kilonewtons already. Moving to point D, at point D it experiences a downward force of 10 kilonewtons. Okay, so minus 10, okay, and this is equal to 0. Take note, at the end of every shear force analysis, and at the end of every bending moment analysis, you must always have 0 as the answer. So let's start the bending moment analysis. Bending moment analysis. Alright, so like I always say, moment of force about any point is always 0. So the moment at point A is equal to 0. So bending moment at A is equal to 0. Between point A and B, there's a UDL. Okay, so we need to form the UDL equation. Now, please take note. This bending moment will be a little bit serious from the rest of them because the UDL is starting from the beginning of the beam. So, which means, and our moment is always from the beginning of the beam to the end of the beam. So, which means we always have the bending moment equation from beginning to the end. So, take note of that. Alright? Moment at A is 0. At the point Fx, at the section Xx, distance x from point A to the point of section. Moment is equal to, first of all, we have a 1.25 kilonewtons force. The moment of this force about the point of section is simply force times distance to the point of section. And distance to the point of section is what? X. So this is upward. Always take note. Upward force should give us downward moment, positive moment, while downward force should give us negative moment during bending moment analysis. Alright, so moments along AB, first of all, 1.25 times what? X. Distance to the point of section. Okay. Now the distance between the UDL and the point of section is what? X. So to convert this UDL to point B, first of all, multiply the distance, the density by the distance x. So in terms of point B, this is minus 2 times x. This is a load and not a moment. Remember. Now you now place this load at the middle of the distance covered by the UDL. In this case, distance covered by UDL is x. Middle of x is simply what? X divided by 2. So this is times x divided by 2. Okay. So this is going to give us 1.25 x minus, of course, 2 and cancel 2. X times x gives us x squared. Alright, so at B, x is equal to the length of the UDL. When it gets to B, x becomes distance from A to point B, which is what? 3 meters. At B, x is equal to 3 meters. So that means moment at point B is 1.25 times 3 minus 3 squared, this is x squared. Okay, so this is equal to 1.25 times 3, it's around 3.75. 3.75 minus 3 squared is 9. Okay, so it implies that moment at B is equal to 3.75 minus 9. Is 5.25 kilo minus 5.25 kilonewtons meter. So that is the moment at point B. Okay, so also since we have the UDL between starting from the beginning of the beam, if we are now moving to the next phase, which is at point C, we also have to take section because of the UDL. So we'll take another section along BC. So taking a section along BC, then the distance of point A, the point of section be x. Okay, always you will do this till the end of the beam. That's where bending moment is a little bit tedious because the UDL is started from the beginning of the beam. So you always take section to the end of the beam. Alright, so taking a section XX from point A along BC, distance from point A to the point of section is x. Okay, first of all, moment of this force about that point of section is force times distance, and the distance it takes this force to get to the point of section remains x. Okay, so we have that moment along this now along BC. Moment along BC is equal to 1.25 times x minus. Okay, so let's do a little mathematics here. We want only the length of the UDL. We want only the length of the UDL, which is 3, but beyond 3, we have already added 1 meters. Okay, to get to point C. It takes extra 1 meter to get to point C. But the length of the UDL itself is 3. And we are simply saying from here, from point A to the point of section is x. We just want the length of the UDL. So we don't need this 1 meters. It means now the length of the UDL is simply what? X minus 1. Because we don't need 1 meter. We just need 3 meters, which is the length of the UDL. So if from here to here is x, length of the UDL alone means you're cutting off from here to the point of section, and 1 meter is from here to point B to point C. So we take off 1 from x. That will give us the length of the UDL. Okay, so we have to convert the one UDL to 1 to 10, we have 2 times the length of the UDL is simply x minus 1. Remember, take off 1 from this x, it will give us the length of the UDL. So multiply the intensity by the length, it will give us the load. Okay, but this is a load, not a moment. Now, after converting this load, place it at the middle of the beam. Remember, you place this load at the middle of the beam. Okay, so to place it at the middle of the length, covered by the UDL. The length covered by the UDL now is x minus 1. Middle of x minus 1 is simply x minus 1 divided by 2. This is the middle of x minus 1. But please take notes. Let me draw it back from here. If this is the middle, we want to take moment about point C. This is point B. We want to take around point C, BC. We are somewhere around there. Middle of this beam, this is the UDL. Middle of this UDL is what? 1.5, 1.5. But moment about point C is actually from this point to point C. That's this load to point C. So the distance between this load to point C is 1.5 plus 1. So after finding the middle, this has to do with the UDL alone. But the moment of the UDL about point C is simply what? 1.5 plus 1. Total distance between this load to get to point C. So we need to add 1 to get to point C. So after finding the middle, add 1 to it to get to point C. Add 1 to the middle to get to point C. That's what happens there. Okay, so after converting UDL to a point load, we now place it at the middle, which is x minus 1 divided by 2. But the moment is going about point C. This is BC, along BC. So we are actually going to take moment about point C. So it takes additional 1 meter to get to point C. So you add that 1 meter plus 1. Okay, so you have that plus 1. Alright, so you have this. Okay? So at C, X becomes, at point C, X becomes the length between point A to point C, which is 3 plus 1, and that's 4. X is equal to 4 meters. So moment at point C is now equal to 1.25 by 4, okay, minus 2 into x minus 1, x is 4 minus 1, all into 4 minus 1 divided by 2 plus 1. Okay, so you have this. Alright, so moment at C is equal to 4 times 1.25. Okay, now this is going to be a little bit tedious and different from the first one because of the UGL starting from the beginning. So, okay, as always introduce your, whenever you see the UGL, there's always a need to bring in the shear force equation. Okay, so to do that, first of all, you must start a section just between the UGL, section XX, before going to the end of the UGL from point A, all the distance towards X to the X. Okay, so shear force analysis. Alright, shear force at A is simply the force that exists at A. Upward force positive, downward force negative. At point A, there is an upward force of 1.25 kilonewtons. So shear force at A is 1.25 kilonewtons. So it's positive. Okay, this same force moves between A and B. So shear force AB, we already have 1.25 moving. But between A and B, there's a UGL. So there's a need to form the shear force equation. We said from point A to the point of section towards X as a distance. So it means now that the point load, remember, if the distance of the UGL is X, then point load is simply the intensity of the UGL times what? Distance. In this case, the UGL load is 2 kilonewtons per meter. Distance now is X. Okay, so we have minus 2 times X. Remember, minus because the UGL load always points downwards. So when it gets to B, notice that X becomes the length of AB. If you finally move from point A to B, X becomes equal to the length of AB, which was 3 meters. So at B, X is equal to 3 meters. So therefore, shear force at point B becomes 1.25 minus 2 times 3, and this is equal to 1.25 minus 6. Okay, so shear force at point B is obviously minus 4.75 kilonewtons. Okay, so this same force moves from point B down to point C. So shear force at C is equal to minus 4.75, but notice that at point C there is an upward force of 14.75 kilonewtons. Upward, so it's positive, plus 14.75 kilonewtons. Okay, so shear force at point C is equal to, of course, minus 4.75 plus 14.75 will give us 10 kilonewtons. And then finally at point D, shear force at point D becomes, okay, so we have 10 kilonewtons already. Moving to point D, at point D, it experiences a downward force of 10 kilonewtons. Okay, so minus 10, okay, and this is equal to 0. Take note, at the end of every shear force analysis, and at the end of every bending moment analysis, you must always have 0 as the answer. So let's start the bending moment analysis. Bending moment analysis. Alright, so like I always say, moment of force about any point is always 0. So the moment at point A is equal to 0. So bending moment at A is equal to 0. Between point A and B, there's a UGL. Okay, so we need to form the UDL equation. Now, please take note. This bending moment will be a little bit tedious from the rest of them because the UDL is starting from the beginning of the beam. So, which means, and our moment is always from the beginning of the beam to the end of the beam. So, which means we always have the bending moment equation from beginning to the end. So, take note of that. Alright? Moment at A is 0, at the point fx, at the section xx, distance x from point A to the point of section. Moment is equal to, first of all, we have a 1.25 kilonewton force. The moment of this force about the point of section is simply force times distance to the point of section. And distance to the point of section is what? X. So this is upward. Always take note. Upward force should give us downward moment, positive moment, while downward force should give us negative moment during bending moment analysis. Alright, so moments along AB, first of all, 1.25 times what? X, distance to the point of section. Okay? Now, the distance between the UDL and the point of section is what? X. So, to convert this UDL to point B, first of all, multiply the distance, the intensity by the distance x. So, in terms of point B, this is minus 2 times x. This is a load and not a moment. Remember, now you now place this load at the middle of the distance covered by the UDL. In this case, distance covered by UDL is x. Middle of x is simply what? X divided by 2. So this is times x divided by 2. Okay, so this is going to give us 1.25 x minus, of course, 2 and cancel 2. X times x gives us x squared. Alright, so at B, x is equal to the length of the UDL. When it gets to B, x becomes distance from A to point B, which is what? 3 meters. At B, x is equal to 3 meters. So that means moment at point B is 1.25 times 3 minus 3 squared. This is x squared. Okay, so this is equal to 1.25 times 3, it's around 3.75 minus 3 squared is 9. Okay, so it implies that moment at B is equal to 3.75 minus 9, is 5.25. Kilo minus 5.25 kilonewtons meter. So that is the moment at point B. Okay, so also since we have the UDL between starting from the beginning of the beam, if we are now moving to the next phase, which is at point C, we also have to take section because of the UDL. So we'll take another section along BC. So taking a section along BC, then the distance of point A, the point of section, the x. Okay, always you do this to the end of the beam. That's where bending moment is a little bit tedious because the UDL is started from the beginning of the beam. So you always take section to the end of the beam. Alright, so taking a section xx from point A along BC, distance from point A to the point of section is x. Okay, first of all, moment of this force about that point of section is force times distance, and the distance it takes this force to get to the point of section remains x. Okay, so we have that moment along this now along BC. Moment along BC is equal to 1.25 times x minus. Okay, so let's do a little mathematics here. We want only the length of the UDL. We want only the length of the UDL, which is 3. But beyond 3, we have already added 1 meters. Okay, to get to point C. It takes extra 1 meter to get to point C. But the length of the UDL itself is 3. And we are simply saying from here, from point A to the point of section is x. We just want the length of the UDL. So we don't need this 1 meters. It means now the length of the UDL is equal to x minus 1. Because we don't need 1 meter. We just need 3 meters, which is the length of the UDL. So if from here to here is x, length of the UDL alone means you're cutting off from here to the point of section, and 1 meter is from here to point C. So we take off 1 from x. That will give us the length of the UDL. Okay, so we have to convert the point median to point to them, you have 2 times the length of the median is simply x minus 1. Remember, take off 1 from this x, it will give us the length of the median. So multiply the intensity by the length, it will give us the load. Okay, but this is a load, not a moment. Now, after converting this load, place it at the middle of the beam. Remember, you place this load at the middle of the beam. Okay, so to place it at the middle of the length, sorry, covered by the UDL. The length covered by the UDL now is x minus 1. Middle of x minus 1 is simply x minus 1 divided by 2. This is the middle of x minus 1. But please take notes. Let me draw you back from here. If this is the middle, we want to take comment about point C. This is point B. We want to take around point C, BC. We are somewhere around there. Middle of this beam, this is the UDL. Middle of this UDL is what? 1.5, 1.5. But moment about point C is actually from this point to point C. That's this load to point C. So the distance between this load to point C is 1.5 plus 1. So after finding the middle, this has to do with the UDL load. But the moment of the UDL about point C is simply what? 1.5 plus 1. Total distance between this load to get to point C. So we need one adding 1 to get to point C. So after finding the middle, add 1 to it to get to point C. Add 1 to the middle to get to point C. That's what happens there. Okay, so after converting UDL to a point load, we now place it at the middle, which is x minus 1 divided by 2. But the moment going about point C, this is BC along BC. So we are actually intending to take moment about point C. So it takes additional 1 meter to get to point C. So you add that 1 meter plus 1. Okay, so you have that plus 1. Alright, so you have this. Okay. So at C, x becomes, at point C, x becomes the length between point A to point C, which is 3 plus 1, and that's 4. X is equal to 4 meters. So moment at point C is now equal to 1.25 by 4, okay, minus 2 into x minus 1, x is 4, minus 1, all into 4 minus 1 divided by 2 plus 1. Okay, so you have this. Alright, so moment at C is equal to 4 times 1.25 is 5 minus 2. 4 minus 1 is 3. Okay. 4 minus 1 is 3 divided by 2 plus 1. So you have this to be 5 minus 2 by 3 is 6. Into 3 divided by 2 is 1.5 plus 1. And this is equal to 5 minus 6 into 1.5 plus 1 is 2.5. Okay. So moment at C is actually 5 minus 6 times 2.5 is 15. Okay, 6 times 2.5 is 15. Therefore, moment at C is minus 10 kilonewtons meter. Finally, moment at point E. Okay, so since there's a UDL from the beginning of the game, like I said, you always take section to the end. Okay, so we also take section about CD. Okay, and the distance from point A simply is x to the point of section. Distance is x to the point of section. Okay, so the moment of this force about the point of section always is the force times the distance. In this case, we are moving along CD. So moment along CD is equal to 1.25 times x. First moment is force times distance. And also the length of the UGL now, since we are now going between CG, we've added 1 and 1, that is 2. But we need only what? 3. So we don't need this one, we don't need this one for the length of the UGL. So it means to move these 2 from what? X. That will become the length of the UGL. So it's simply x minus 2 becomes the length of the UGL. Alright? So on getting that, converting the UGL, the point load now becomes minus the intensity of the UGL, which is 2, times the distance, x minus 2 in this case, is the point load. Then we place this point load at the middle of the length covered. So x minus 2 divided by 2. But it doesn't end there. After placing it at the middle, remember it is somewhere around there, which is 1.5 from here, okay, to point B, 1.5. We are considering what? Moment to point D. So we now have to add 1 plus 1 to get to point D. So which means 1 plus 1 is 2. So we are adding plus 2 to obtain the moment of this force from the middle of the length of our medium to point D. So middle is 1.5. 1.5 till point D means addition of 1 plus 1, which is 2. So we are now adding plus 2. Okay, so that is it for the UDL. Also notice that there is another force 14.75 kilonewtons. Since the distance from here to here is x, we need only distance from 14.75 down to this point. So which means we don't need this whole distance from here to this point. We are now at point C, from point C to this point D. We don't need from this side down. So the distance we have left down here is 1 plus 3, which is 4. So we are removing 4 from what? X to obtain distance from this force to this point. Alright, so we have all 4, so it's positive plus 14.75 into x minus 4. And that's along C. So at D, we have that x becomes the length of the beam, which is 3 plus, which is 5. At D, x is equal to 5. So the moment at point D will give us 1.25 into 5 minus 2 into 5 minus 2 into 5 minus 2 divided by 2, okay, plus 2 plus 14.75 into 5 minus 4. And this is equal to 1.25 by 5 give us 6.25. So we have 6.25. Okay, minus 2 into 5 minus 2 is 3 into 5 minus 2 is 3 divided by 2 plus 2, okay, plus 14.75 into 5 minus 4 is 1. Okay, this is equal to 6.25 minus 2 by 3 is 6 into 3 into 2 is 1.5 plus 2 is 3.5 plus 14.75 times 1 is 14.75. This is equal to 6.25 minus 6 times 3.5. 6 times 3.5 is 21 plus 14.75. Moment at D is equal to 6.25 minus 21 is minus 14.75 plus 14.75. Therefore, this bending moment is 0. Again, at the end of every bending moment analysis, you must always obtain 0 as the answer. So let's draw the diagram and see. So break down our beam. RAY give us 1.25 kilonewtons. This point A. Between point A to point B, we have a UGL. The intensity is 2 kilonewtons per meter. At point C, we had an upward force of 14.75 kilonewtons. At point B, also an upward force of 10 kilonewtons. trace each point down. And I will always say, trace each point down. Trace each point down. This is point B. This is point C. Okay, so let's start with the shear force. The highest value for the shear force is 1.25, I guess. 10 kilonewtons is the highest value for the shear force. So we have 10 kilonewtons. So let's call this point our zero mark. So this is our origin, 0. Above positive, below is negative. So we have 10 kilonewtons as the highest value for the shear force. That shear force at point C. So let's call here 10 kilonewtons. Okay. The next value we have is 1.25. Next highest value is 1.25 kilonewtons. So we have 1.25. Let's call here 1.25 kilonewtons. And then we have minus 4.75 kilonewtons. Minus is down, so minus 4.75 kilonewtons. Have this. So let's trace each point out. Okay, trace each point out. Trace each point out. Shear force at A is 1.25 kilonewtons. This is line A. This is 1.25. You can tell it. Shear force at B is minus 4.75 kilonewtons. This is line B. This is minus 4.75. You can tell it. Shear force at C is 10 kilonewtons. This is line C. This is 10 kilonewtons. This is C. You can tell it. Shear force at D is 0. So this is line D. This is 0 line. You can tell it. Okay, from point A we have a point unit of 1.25 kilonewtons from the origin. So point unit, shear force of point is always a straight line. So connect. Now between point A and point B, there's a UGL. And UGL is usually the shear force diagram for UGL is usually a slant line. So you slant the line and connect the dots. You have this. Okay. This then shear force moves from point B down to point C. Yes, down to point C. At point C, we encounter an upward force of 14.75 kilonewtons. So we connect. Upward force of 14.75 kilonewtons. So we connect down to 14.75. This then force moves from point C to point B. And then at point B, we encounter a downward force of 10 kilonewtons. So this is what the shear force diagram looks like. Alright, so this is shear force diagram, SFD. Bending moment diagram. Let's check the bending moment analysis. The highest value for bending moment is negative. This is negative. This is also negative. So we have negatives, and then we have 0. So minus 10 and minus 5.25. So minus 5.25 is the highest value for the bending moment. So this is our 0 line. This is our 0 line. Minus 5.25, all is here. Minus 5.25 kilonewtons meter. And then we'll add minus 10 kilonewtons meter. So trace out each of the points. Trace out each of the points. Bending moment at point A is 0. This is line A. This is 0 line, so we have steps. Moment at point B is 5.25 kilonewtons. Minus 5.25 kilonewtons. Moment at point B. This is line B. This is 5.25, so we have steps. Moment at point C. Moment at point C is minus 10 kilonewtons. So this is line C. It's minus 10 plus 30. Okay, moment at D is 0. This is line D, this is 0. You are 30. Okay, so between A and B, there's a UDL. And of course, UDL. Okay, so we have a curve. In this case, take note this curve. Okay, we have a curve connecting point D, point A to point B. Okay, now between point B to C is a point node, so point nodes are slant lines. You have this, and then you have this slant lines. Okay. So this is the bending moment diagram. So this is the curve. This is for the bending moment diagram looks like. So this is the bending moment. Alright guys, till I come your way with another amazing question on shear force and bending moment analysis. Please don't forget to subscribe to my channel, and of course invite your friends to subscribe to my channel as well. I'll see you in the next video. Cheers.